As an introduction to the last set of topics we're going to talk about, I want to think about conic sections today. I'm going to take a right circular cone, make a copy of it, join the points together, and I want to think about what sort of shapes I can get if I intersect this with a plane. I think it's fairly clear that if I make my plane at right angles to the axis of symmetry to the cone, I'm just going to get a circle. If you tilt the plane, but don't tilt it very much, you're going to get an intersection that sort of resembles a circle, but is longer in one direction than the other. If I were to use a vertical plane, or even a plane that was almost vertical, I would have two distinct chunks, one up above and one down below. The name of that shape is a hyperbola. And if I rig it carefully so that my plane is parallel to one of the sides of the cone, I get one piece, unlike the two pieces that you had in the hyperbola. But unlike the ellipse, it doesn't join back up at the end. So I end up with some shape like this, which we will call a parabola. The ancient Greeks liked to think about geometry like this. We use geometry also quite often, but we use it in the analytical geometry sense. We have formulas and equations that will relate variables together. So we're going to have a second way of thinking about these different categories of shapes, these conic sections, which we'll talk about now. The other way that we can think about these things is in terms of distances. You can define a circle to be the set of all points that are the same common distance from some particular fixed point. The fixed point is the center of the circle. The common distance is the radius. When we do our analytical geometry, we use pairs of numbers to represent points. So the center of the circle, I'm just going to make up letters to call the coordinates H and K. A point that is going to be on my graph of my circle, I'm just going to call its coordinates generically X and Y. And you'll remember the distance formula. You take the difference of X, difference of Y, square them, add them up, and do the square root. So if you literally do that, you get this equation, and it's traditional to square both sides of the equation. And if you do that, you get back our familiar equation for a circle with center at point HK, radius R. We've seen this many times before. What we would like is to get similar formulas, similar equations that are going to represent an ellipse, a hyperbola, and a parabola. So we're going to have some definition that involves distances and points. In the case of an ellipse, there's going to be two fixed points, not just one, like for the circle. We call these points foci, which is the plural for focus. We're going to have a point, P. I'm going to measure the distance from one focus to P, call that D1. Measure the distance from the other focus to P, call that D2, and we want the sum of these two distances to be a constant number. So the equation that we're going to get for the ellipse is going to be D1 plus D2 equals constant. If I were to call this distance D1, the equation for the circle just said D1 is a constant. For the hyperbola, we're going to have two foci again, just like we did with the ellipse. From one focus to the point of interest, we'll have D1. from the other focus to the point of interest D2, the hyperbola is going to be defined not by distance is a constant or the sum of the distances is a constant. The hyperbola is going to have the difference of the two distances a constant. And for the parabola, we will have one focus, but we also have a new feature. We have a straight line that doesn't pass through the focus. We call that straight line the directrix, and I calculate the distance from the point that I'm interested in to the focus, calling that D1, calculate the perpendicular distance from the point of interest to the directrix, call that D2. The parabola is going to be the set of all points where those two different distances are equal to each other. Generally speaking, it's a bad idea to assign an algebra letter to one specific thing and keep it that way always. In this particular case, we're going to go against that though. If I have an ellipse, I'm going to look at the long axis and I'm going to call that length 2 times A. So the length of the major axis is 2 times A. Semi-axis would be A then. The distance between the foci, I'm going to call 2 times C. If I look in the right angle direction, I'll call the biggest length in the right angle direction that I can get 2 times B, that's the minor axis. And I want to think about how distances are related to each other here. I've drawn my original picture tilted, so I won't be biased as to whether the long axis is horizontal or is vertical, but I'm going to start drawing things one way or the other now. For right now, I'll draw it horizontal. This is the center of the ellipse, and if I go all the way to the right as far as I can, I've got a distance of A. If I sit in the middle and I go to one of the foci, I've got a distance C. So the distance from this focus to this point must be A minus C. Also, if I start here and go as far to the right as I can, I have A units of distance, and then an additional C units of distance here. The distance from this particular point to the other focus is A plus C. The sum of the distances is A minus C plus A plus C, which is 2A. I need to know that because when I want to write down the equation for my ellipse, it's going to be, in general, distance 1 plus distance 2 equals a constant, and I need to know what the constant is. It's 2 times A in this case. There's a relationship between the numbers A, B, and C that we can figure out by thinking not of that particular point, but of that one instead. Here I have a right triangle, so it follows that D1 squared must be this distance squared, B squared, plus this distance squared, C squared. On the other hand, this triangle is the mirror image reflection of that triangle about the y-axis. So without any extra work, D1 squared and D2 squared are the same number. They're B squared plus C squared when I'm looking at this particular point. D1 equals D2, which is B squared plus C squared. So D1 plus D2 must be 2 times square root B squared plus C squared. On the other hand, when we were looking at this point, we figured out that D1 plus D2 has to be 2 times A. So this number and that number have to be the same thing. get rid of the 2, square both sides. People usually write this with the c squared over on the left. C squared is a squared minus b squared. So there's a relationship between these 3 numbers that we've figured out by looking at a certain particular point. The eccentricity of the ellipse is how far apart the foci are divided by the length of the major axis, which, if you wanted to be picky about it, is 2c over 2a. Of course, you can cancel the 2's out. The eccentricity is c over a. This gives me a measure of how different from a circle this is, a measure of how elongated the ellipse is, if you want to think of it like that. How are we going to get the equation for an ellipse? We're going to write down the defining characteristic for our ellipse, which is d1 plus d2 equals 2a, and then we're going to do a fairly large amount of algebra. No one step of this is hard, it's just that it goes on for a while. So we're going to absolutely literally do this. D1 is the distance from xy to that focus, which is negative c for the x coordinate, 0 for the y coordinate. D2 is the distance from xy to the other focus, x equals c, y equals 0. Putting the coordinates into the distance formula, D1 is radical of x plus c squared plus y squared, and D2 is radical x minus c squared plus y squared. And what we want is D1 plus D2 equal to 2 times a. Now that formula is very easy to write down, but there's a problem with it. It's expressed in an extremely awkward way. There's 2 square roots in it. It's very complicated looking, so we need to work on this a little bit. What we'll do is we'll subtract this term over to the other side. By doing that, I get one of the square roots by itself, which means if I square both sides, at least one of the square roots will go away. So over here, the square root goes away. When I square this difference, it's the square of the first term, the square of 2a, which is 4a squared, minus 2 times the first term times the second term. That's where the 4 comes from. 4a times radical x minus c squared plus y squared, plus the square of the other thing, and all that does is get rid of the square root symbol on it. Multiply everything out. X plus c squared is x squared plus 2xc plus c squared, and then I have my y squared. X minus c squared is found in a similar way. And if you notice, there's a term over here of x squared, and there's a term over here of x squared. Subtract x squared from both sides, and the x squares disappear. The same thing happens to the c squared and to the y squared. So big chunks of this will disappear. All that's left is 2xc is 4a squared minus 4a times this radical symbol minus 2xc. There's a 2xc on both sides, but over here it doesn't have a minus sign on it, and over here it does. So if you'll add 2 times x times c to both sides, that gets rid of this and turns this into 4 times x times c with the remaining 2 terms. Everything has a factor of 4 in it now, so subtract 4 from everything. Oh, pardon me. Divide both sides by 4 to get rid of the 4. rearrange that equation until the chunk with the single remaining square root in it is all by itself, and then square it again. I'll have a factor of a squared. I'll have a factor of that squared, and all that's going to do is get rid of the square root sign finally. If you square this, again, it's the square of the first term minus 2 times the first term times the second term plus the square of the second term. So this is just routine algebra here. Expand out the x minus c squared, x squared minus 2xc plus c squared, and don't forget the y squared. Distribute the a squared through. Another miracle happens. 2 times a squared xc shows up here being subtracted away, and it shows up here being subtracted away as well. If you'll add 2a squared xc to both sides, it goes away completely. Over here, I've got an x squared term, but it's got a coefficient of c squared on it. I'm going to subtract that away to put it with the term on the right. Here, I had a squared x squared, and I'll have minus x squared c squared. So we will have a squared minus c squared x squared. I have a squared y squared, and all that's left is a squared, assume a to the 4th power that is, minus a squared c squared, having moved this term over to the right. I'm making it look more simple. I'm trying to make this look as much like the equation of a circle as I can manage. A to the 4th minus a squared c squared, I'm going to factor this. That's a squared times a squared minus c squared. And things are beginning to look up because there's an a squared minus c squared over here, and there's an a squared minus c squared over here. I can't just cancel it out because there's no such factor here, but I'm going to do something with it. We figured out that there's a relationship between those 3 numbers, a, b, and c. C squared is a squared minus b squared, which tells me c squared plus b squared is a squared, which tells me that a squared minus c squared is that other distance squared, b squared. So if you write that in, all of a sudden, our formula is getting much simpler looking than it used to. The way people usually write this kind of thing is they rig it so that there's a 1 over on the right-hand side. To do that, divide both sides by a squared times b squared. In this term, the b squared cancels out. In that term, the a squared cancels out, and that's 1. So the equation for my ellipse is x squared over a squared plus y squared over b squared equals 1. For an ellipse with its long axis along the x-axis and center at the origin, this is going to be the equation of my ellipse. I have a direct significance for what that a is. That's how far out from the middle a point on the ellipse can be. At the moment, this b, all I know about it is it's the short distance. So this is easy to think about. When we do the corresponding thing for the hyperbola, the b is going to be a little bit of a mystery. So when I say this is both easy and horrible, it's easy because no one step of this is very difficult, but it goes on for quite a while. Side comment, suppose a and b were the same number. X squared over a squared plus y squared over, if a and b were the same number, b squared would be a squared. multiply both sides by a squared, and you see that's the equation for a circle, center at the origin, radius a, which is at least some reassurance that this result is probably right. So we know all about circles, and now we know all about ellipses that are like this. I said that the a number was going to be related to the long length of the ellipse. We'll use the a underneath the x squared here, because x is the axis along which the long axis of the ellipse lies. So this is going to be our equation for such an ellipse, and c squared is going to be a squared minus b squared. And you see it's important that the a be bigger than the b because c squared can't be negative. The eccentricity is c over a. For example, x squared over 9 plus y squared over 4 equals 1. A squared is 9, so a is 3. B squared is 4, b is 2, and I'd like to calculate the location of the foci. C squared is a squared minus b squared, bigger one minus smaller one. C has to be square root of 5. Also, now that I know that, the eccentricity is square root of 5 over 3. Square root of 5 is about 2.23 some odd. So the distance between the foci is smaller than the distance between the vertices, as we're going to call them, 2c divided by 2a. For an ellipse, this eccentricity that we're going to calculate is always going to be between 0 and 1. If the long axis were along the y-axis, I'd call this distance a and this distance b instead. So the equation would be y squared over a squared plus x squared over b squared equals 1. And the reason is the same as before. I want to be able to calculate the location of the foci, using that same formula. And the eccentricity is c divided by a again. So really, it's immaterial to us whether the long axis is vertical or horizontal. We just have to keep straight where the a goes. I should at least mention people use the usual approaches to learning this stuff. They make you work various problems that are really basically busy work from our point of view, but I feel like I ought to do at least one of them. So suppose you have an ellipse with the center at the origin. The long axis is horizontal. The point x equal 4, y equal 1 is on the ellipse, and the eccentricity is 1/3. I want to find an equation for the ellipse. Because the long axis is along the x-axis, I'm going to write my equation as x squared over a squared plus y squared over b squared equals 1. I know something in particular. I know that when x is 4 and y is 1, I'm supposed to be on this ellipse. 4 squared is 16, 1 squared is 1. We have an equation that relates the a and the b. We know something else too. The eccentricity, which is c over a, is 1/3. That tells me that 3 times c equals a. That says 9c squared is equal to a squared. But c squared, remember, is a squared minus b squared. So put that fact in, rearrange it, and I find out that 8 times a squared has to be 9 times b squared, and I've got a second equation now. The only things in this whole situation that I don't know are a and b. I have 2 equations that relate A and B, if there's any luck at all, we ought to be able to solve these equations and figure out what the A and the B are. Using that second fact, A squared has to be 9B squared over 8, and I'm going to write that fact down into the first of our two equations. It's kind of messy looking. Multiply both sides by 9B squared over 8. Here, I just have the 16 left. Here, I have 1 over b squared times 9 times b squared over 8. And here I have 1 times 9b squared over 8. A miracle happens. The b squareds cancel out in this piece. Over on the other side, I have a b squared multiplied by 9 and divided by 8. I could deal with it as is, or I could clear the fractions again. Multiply both sides by 8, and it turns out that 9b squared has to be 137. That says that b squared has to be 137 divided by 9. The second that I know that, I go back over here to this formula. A squared has to be 9/8 times 137 over 9, which is 137 over 8. I made this problem up so the numbers didn't come out nice looking. Even so, the equation for the ellipse is x squared over a squared plus y squared over b squared equals 1. And we now know what a squared and b squared are. Here's my equation for my ellipse. Now, this is all very convoluted, and I want to make sure that my answer is right. On the ellipse, the way we've got it orientated, if x is 4, there's going to be probably 2 places on the graph to go with that. I'd like to locate them, and I'd like to make sure that one of them is the y coordinate that I ought to be getting. So I took the calculator and calculated these numbers. It turns out, after you do the algebra, that y squared over 137 over 9 is 0.0656934,307. When I multiply both sides of the equation by 137 over 9, what happens on my calculator is it tells me that y squared is 1, which tells me the y coordinate of that point is 1. The y coordinate of that point's -1. The other one doesn't bother me. It's getting that one that's important to me. So this is an ellipse. It has the correct point. And if you calculate the eccentricity, you'll find out that that's correct too. Now for the hyperbola, I'm going to have 2 fixed points, the foci of the hyperbola. The distance between them, I'm going to call it the same thing I called it for ellipses. I'm going to call it 2 times c. There are going to be 2 turning around points, if you want to think of it that way. Those are going to be called the vertices of the hyperbola, and I'm going to call the distance between those 2 times a. This time, it's not d1 plus d2 that needs to be 2 times a, it's d1 minus d2. I'm not going to make you suffer through the algebra again, but if you wanted to, you could go back to my ellipse calculation, and where it says d1 plus d2, erase the plus sign, put in a negative sign, and then do all of that horrific algebra again. But the result is this. The points that obey d1 minus d2 equals 2a obey the equation x squared over a squared minus y squared over b squared equals 1, where c squared this time, for ellipses, it was a squared minus b squared. For hyperbolas, It's c squared is a squared plus b squared. I'm thinking in this case about the horizontal axis situation. The a tells me where the hyperbola cuts across the x-axis. The c are the foci. The role played by the b is not clear at all now. In the case of the ellipse, it was the length of the semi-minor axis, but for hyperbolas at this moment, we don't know what the b means. We'll figure that out in a moment. And as I said, if you don't believe this, go back and write down the appropriate equation that represents d1 minus d2 equals 2a, and then suffer through about 3 pages of algebra, but this will be the conclusion that you're led to. In the ellipse, the a went with the variable that corresponded to the long axis. That is not true for hyperbolas. The a is going to go with the variable where you get intercepts. So if I had a vertical hyperbola like this, it cuts across the y-axis at y equal a, and also at y equal negative a. The a squared is going to go underneath the y squared, not the x squared. So the equation of such an ellipse would be y squared over a squared plus x squared over b squared equals 1. And really, it doesn't matter to me which one is the bigger one and which one is the smaller one, because to get c squared, I'm not subtracting anything, I'm adding them. So the only reason that we need to keep this distinction is that the eccentricity is still c divided by a. So I have to interpret the a correctly. The b, we have no idea what the b is at the moment. I want to look at a specific example of one of these hyperbolas where the a goes with the x. So this is going to be x squared over 4 minus y squared over 9 equals 1. A squared is 4, y squared is 9, a is 2, b is 3. If I go looking for intercepts, I'm looking for places where y equals 0 on this graph. That'll give me the x-intercepts. The equation says x squared over 4 is 1, which obviously means x could be 2 or negative 2. So I'm going to have 2 x-intercepts here. What about trying to take x equals 0 in this equation? That would say the negative of y squared over 9 was 1. That would say the negative of y squared is 9. That would say y squared itself is negative 9, and that doesn't happen in the real number system. I want to think of this in a slightly different way. I'm going to get the y by itself, and then I'm going to factor up the inside here. I'm going to factor x squared over 4 out of it. So y is either 3 radical x squared over 4 radical 1 minus 4 over x squared, or the negative of that. The reason that I want to think about it like this is when x is big, when the point you're talking about is far away from the origin, 4 divided by x squared is going to be very small. The further out you get, the smaller it'll get. The quantity underneath the square root sign here is 1 minus something that's really small if I'm far away from the middle of the picture. So if absolute value of x is really big, y is approximately plus or minus 3x times 1. If I'm far away from the middle of the picture, the hyperbola has to start looking very much like a straight line. These lines are called the asymptotes of the hyperbola. And you'll notice the B and the A both show up in this equation. This is the role of the B. It ends up indicating what the asymptote is. I can figure something else about this graph out too. Take the original equation, x squared over 4 minus y squared over 9 equals 1, and I'm going to do implicit differentiation on it. I'm going to differentiate with respect to x. Derivative of x squared is 2x, and y, which I'm going to think locally at least as being a function of x, has derivative of y squared equal 2 times y times dy dx. This is the chain rule. If you rearrange this, dy dx is 9/4 times x over y. You might be thinking the derivative will be 0 at x equals 0, but that's not right, because if you remember what we said, when x is too close to the origin, if x is very small, the number underneath the square root sign is going to be negative, and I'm not going to get a point on the graph. So x equals 0 is really a non-issue that doesn't happen. Y equals 0. If y equals 0, then I'm going to have x equal plus or minus 2. I am going to have vertical tangent lines, but it only happens in 2 places, namely the turning around point on this graph. So there are no maximums and minimums, no local high or low spots, and the only place where the derivative acts badly is when it's vertical. And if I'm far enough away from the middle of the picture, the graph has to look like y equal 3/2 x or negative 3/2 x. There is no wiggle room left now. This can't have any high or low spots. It has to look like this straight line down here. It has to look like that straight line up here. I have to have a vertical tangent line there. There's absolutely no wiggle room in saying what this has to look like. And thinking in a likewise manner, this has to look like this. This is what my hyperbola is going to look like. If I wanted to calculate the C, you could do that. If you want to calculate the eccentricity, you could do that as well. For an ellipse, the eccentricity is always less than 1 because C is less than A. For a hyperbola, the ellipse is always bigger than 1 because C is always bigger than A on a hyperbola anyhow. As a sanity check, I'm going to draw the graph of y equals 3 times square root of x squared over 4 minus 1. I'll also draw the graph of y equals the negative of that. Also, I'm going to draw in the 2 straight lines that I think my graph has to start looking like as I get away from the middle of the picture. I'm going to put this on the standard viewing window. So there's the top. Here comes the bottom of the hyperbola. And here are the first asymptote followed by the second one. It looks exactly like we figured out that it was going to look, as it should. I have to make a comment here though. I'm going to zoom in. Now, I know for a fact that this hyperbola touches the x-axis at x equals 2 and x equals -2. But if you look closely at the picture on my calculator screen, it says that it doesn't. It says that there's this gap between the upper part and the lower part. That gap is not there. This is a failure of the algorithm that your calculator uses to plot things. Not all calculators fall victim to this. Some do, though, but be aware there are no gaps like that in the graph of a hyperbola or an ellipse or a circle or any of the conic sections, really. And lastly, I'm just going to say a few words about the parabola. It's going to have kind of a U shape to it. It's going to have one turning around point that I'll call the vertex. I'm going to draw my coordinate system so that the vertex is at the origin. So a point on my parabola is going to be at the origin here. A parabola is the set of all points that are equidistant from, firstly, the focus, and secondly, the directrix. So I will use the distance formula to calculate this distance. The other one is easier to get than that. So D1 is going to be the distance from the focus to the point XY that I'm interested in. The focus is located at x equals 0, y equal p, so it's a simple matter to write those down and get a formula for D1. D2 is actually easier than that. This distance is y, and I have to have the vertical distance from the x-axis to the equation of the line being y equal -p. Distances are not negative, so I'm going to have p more units of distance. So D number 2 is just y plus p. The parabola is going to be determined by D1 equals D2. I'm actually going to work the algebra out, but unlike what happened with the ellipse and would happen with the hyperbola, this is not too bad. So again, being literal-minded about it, distance 1 equals distance 2. This time there's only one square root running around in it, so that's why it's not going to be so bad. Square both sides, and then write out what y minus p squared is. It turns into x squared plus y squared minus 2yp plus p squared equals y squared plus 2yp plus p squared. There's some things underlined here. There's a plus y squared over here, and y squared is a term over on the right. If you subtract y squared from both sides, the y squared piece goes away. If you subtract p squared away from both sides, it goes away too. The only thing that's left is x squared minus 2py equals 2py. If you add 2py to both sides, you find out that x squared and 4 times p times y have to be the same thing. This is going to be the equation for our parabola. In particular, if you let p equal 1/4, then that equation for the parabola reduces down into y equal x squared, which is what people usually think of first when somebody mentions a parabola. There's a lot more you could say about conic sections, but for our purposes, I believe this will be enough. So in the next discussion, we'll start talking about parametric equations and parametric representations of curves.